Hello class, in this video we're going to be looking at heating curve calculations. So we're going to be doing a little bit of math today. Before we do, I just wanted to get a couple definitions down. First one is the molar heat of vaporization, and we'll talk more about what this means, but here's a definition. It's the amount of energy needed to vaporize 1 mole of liquid. So that just means take 1 mole of liquid and you want to turn it into a gas. How much energy does that take? And this is in the units of kilojoules per mole. And the next definition on the same page here is that we have the molar heat of fusion. So this is the same type of thing, except for this is the amount of energy needed to melt 1 mole of a solid. So you take a solid and you're turning it into a liquid. How much energy does it take to melt that 1 mole? And this is again in kilojoules per mole. So we need one more definition. The next definition here is the specific heat capacity, was the amount of energy needed to raise 1 gram of substance by 1 degree Celsius. So now we know how much energy it takes to melt a mole of a substance, then raise that temperature of that gram of substance and vaporize it. So if we look at a heating curve, we can see on the heating curve here that we have specific heat right here. So how much energy does it take to heat up this ice to this melting point? Once it gets to the melting point, the heat is converting the ice into liquid water, melting it here. That would be the heat of fusion. Then we have a specific heat of raising the water up to the boiling point. And then we had the heat of vaporization here, so that that heat is being applied to vaporize the water. And then when we have water vapor here, we can increase the temperature of water vapor based off its specific heat. So here are our equations that we're going to be using, are these two different equations. So the tough part is determining which one am I going to use. Am I going to use this one here? Heat equals moles times the heat of vaporization. This could also be replaced with heat of fusion. Or is it going to be heat equals the specific heat times mass times the change in temperature? Notice that in this equation here we're dealing with the substance in a mass, and here we're dealing with the substance in a mole, in moles. So we have to be careful of that. We're going to have to maybe change a mass into a moles and then back again. So let's look at a couple of examples and get some practice. Alright, so let's look at our first example here. The first one says, how much heat is needed to boil 3.4 moles of water? So your very first step is to figure out which equation are you going to have to use. You may even have to use both. And then so you're going to have to figure out which order you're going to need to use it in. For this particular problem, we're talking about boiling 3.4 moles of water. So we need our heat equals moles times the heat of vaporization, because that's all we're looking at. We're not looking at how much energy does it take or how much heat does it take to raise the temperature of this water, just boil the water. So we're assuming that the water is already at the boiling point. So this is the equation that we're going to use. The heat equals the moles times the heat of vaporization. And that's what we're looking for. So let's write out heat is equal to the moles we have right here, 3.4. That's moles. And we have times the heat of vaporization, and they give that to us here. That should always be given to us unless we're trying to figure it out. And that's going to be 40.79 kilojoules per mole. And then at this point it's just multiplying. So pretty easy. Let me get my calculator out. Let's see what we got here. We have 3.4 times 40.79 equals, and we have 138.686. We need to put in the right sig figs. so there should be only 2 sig figs there, so 140, and our units here, the moles, will cancel each other out, so this will just leave us with kilojoules. So that would be our answer right there. 140 kilojoules of heat is needed to boil this water. Alright, so let's look at our next example. So in our next example here, it says how much heat is needed to raise the temperature of 15 grams. So we have 15 grams of water by 45 degrees Celsius. So they don't give us a starting point, they don't give us an ending point. We know that it's water. I guess I'm assuming that it's liquid water, it's not ice or steam. I guess they would say that. They give us the specific heat of water, which we have right here, 4.18 joules per gram centigrade. So now we have to figure out what equation do we need. Well, we're trying to raise this temperature. We're not trying to boil it, we're not trying to melt it, so we're just trying to raise it. So we're just going to use this one here. The heat equals specific heat times the mass times the change in temperature. So now that we know what equation we're going to use, we want to make sure everything's in the right units. We need temperature to be in Celsius, which it is. We need our mass to be in grams, which it is here. And we need our specific heat, which we have. Alright, so we're ready to start. So we know that the heat is equal to the specific heat, which we have is 4.18 joules per gram centigrade here, times the mass, which is 15 grams, and times the change in temperature, which is 45 degrees Celsius. So again, you just have your calculator. Shouldn't be too tough here. We have 4.18 times 15 times 45 equals, we have 2,821.5. We have 2 sig figs here, so that's going to be 2,800. What's the unit? Well, we have our grams and our Celsius chain cancel all out, so this is going to be in joules. That shouldn't be equal sign, sorry. 2,800 joules equals my heat. Alright, so let's look at one last example here, and in this example we're probably going to use both equations here. So in this example we have how much heat does it take to raise 36 grams of ice to 55 degrees Celsius. So we have 36 grams of ice here, and we're raising it from -15 all the way to 55. So we know that's going to go past its melting point. So we have to take this here to get it from -15 to 0 degrees. Once it gets to 0 degrees, then we have this heat here of vaporization, but it's not going to be vaporization, it's going to be fusion here. And then it goes back down here to the specific heat, but then we're going to have water instead of the specific heat of ice. We're only going to be able to use that for ice. Remember, the water was, from the previous example, 4.18 joules per gram Celsius. Okay, so this is going to take a little bit of work. So what you want to do is just kind of separate these two into two different equations, do the 2 different equations, and then add the 2 answers at the end. Or maybe even 3 answers for this one. So let's first see how much heat does it take to raise ice from -15 to 0 degrees Celsius. So that would be this first equation here. So we have the heat is equal to the specific heat, and we have the specific heat here of ice, 2.0 5. We have the units there, times the mass, which is 36 grams, times the change in temperature. The change in temperature is going to be 15 degrees to get from -15 to 0 degrees Celsius. So that's going to be the first equation there. That's just to get to 0. And then we got to melt the ice. So we need this equation here, where we have heat equals moles times the heat of vaporization, or heat of fusion. In this case, we're going to use heat of fusion, which is right here. So we have heat is equal to, but we need this mass in moles. We have 36 grams, but we need it in moles. The molar mass of H2O is 18.02. Let's just use 18 just to make this easy. So we have 2 moles. 2 moles times the heat of vaporization. We have right here, or excuse me, heat of fusion. So we have 6.03 kilojoules per mole. So now we have liquid water. And then we have to bring that liquid water up to from 0 to 55 degrees Celsius. So we have another heat is equal to, and we're going to use the specific heat here equation here. So we have the specific heat of water, liquid water, 4.18. We have the units there. Times, now we're using mass again, so 36 grams. Times the change in temperature. Well, we started at 0, now we're going up to 55, so it's a 55 degree change. So now we're going to have to plug these in the calculator and figure them out. Make sure that you're keeping your kilojoules separate from your joules, and then we're going to have to do some rearranging there. So, get my calculator out. We have 2.05 times 36 times 15 equals, using 2 sig figs, 1100, and that is in, those will cancel, joules. Next one, we have 2 times 6.03 equals, so we're going to have 12,000 joules, because it was 12 kilojoules. So those are the same. I'm just keeping it in joules so we can add these at the end. And then our last one here, 4.18 times 36 times 55 equals, and we have 8,300, and that's in joules. So these will cancel here. Yeah, that's in joules. So then we can just add up all my energies here, and that's going to be the total energy. So I have 1,100 plus 12,000 plus my 8,300. And we get 21,400 joules. So that would be my final answer. So you can see how sometimes they get a little bit more complicated, but the math involved is not all that difficult. So hopefully you enjoyed this video, and we'll bring questions back to class. Thanks.